Okay. Yeah, in the last video 4, I had mentioned that we'll go a little bit up. What happens when theta by 2 equal to alpha? I got all excited. What I had in mind was actually the special case theta equal to alpha, but somehow I made some statements with theta by 2 equal to alpha, so you can disregard that. Theta by 2 equal to alpha is a situation where gamma, which is theta by 2 minus alpha, becomes 0. So therefore this is a case where G and H coincide with O4, and therefore the two circles that we showed. So let me backtrack a little bit. You remember we had these two circles. One was a B1 dash circle, which is the top one, and then we have a B1 circle, and that is because G and H were separated out. Now in this special case, we have both of these coinciding. Therefore, as a consequence of that, we have a G and H coinciding with O4. The two circles collapse into a single circle. So when theta by 2 equal to alpha, you don't have two circles to choose from, you have one circle. And again, you draw those two lines that like we showed before. Let me go back and show that thing again. How do we decide? We draw with respect to O2, O4 a line at theta. In this case, we are doing with 70 degrees, one more theta from this side. So what happens is that in this particular case, this collapses, so we don't have the two circles, so they will kind of coincide. So again, from this point forward, you can have B1 prime, and from this point to this, we can have B1. So that remains as it is. So the allowable region essentially would be going from here to here, and for B1 dash, essentially from here to here. Sorry. So that's what we have. So effectively, it will look as though there are no gray areas, but you have to keep that in mind. Okay, all right. The more interesting case is when theta equal to alpha. Okay, what happens when theta equal to alpha? Let's look at that, visualize that scenario. Now theta by 2 minus alpha is minus alpha by 2 for alpha positive. It's a negative number, which means that from O2 we have to draw a line which is anti-clockwise at alpha by 2. So which is what I have drawn here. So this line is an angle that is drawn at alpha by 2, and therefore remember, in order to find G, we have to draw another line from O4, which is counterclockwise to O2 O4 at an angle alpha by 2. So it turns out that these two lines are going to be parallel, which means that my G is at infinity. All right, and in order to locate H, we have to locate, so G will be at infinity somewhere there. So we now project, since H is found by reflection, so we reflect about O2 O4, so we have another line at alpha by 2 over here, and H will be at infinity corresponding to that. So that is how we locate the centers. They are actually at infinity. So what happens to the circles? So the center G is at infinity. The B1 dash locus becomes essentially a straight line. So we have in this particular case, as G goes to infinity, earlier we had G and H coincide with O4 for theta by 2 equal to alpha. When theta equal to alpha, the centers of the B1 dash and B1 circle move to infinity, which means the circle becomes a straight line like this, which is perpendicular to this line drawn at alpha by 2 in a counterclockwise sense. So B1 dash locus is a straight line perpendicular to this magenta purple line, and similarly the other center is reflected about O2 O4 and is also at infinity. So therefore, so that was drawn by marking this angle alpha by 2. So you had H at infinity. Again, B1 locus will be perpendicular to H, the line on which H is located, and it turns out that the angle between the B1 dash locus and B1 locus is going to be theta, which is equal to alpha. So these two straight lines coming off O2 are the loci of B1 dash and B1. So the circle has now become a straight line, which is the infinite radius situation, right? Remember, an infinite radius link essentially is like a slider, so you have a straight line motion or a translation. Um, Now you can pick any point B on this B1 locus, right? So I can pick, so I can arbitrarily pick some point here or some point there, and then of course join O4 to that point, and then with that as the radius, draw an arc, and then get the corresponding point on the B1 locus. So let's do that. So if you do that, I get a design. So here's what I have done. I have just arbitrarily picked a point B on this B1 locus, and then from there, so this distance is 50.7 millimeters or 5.07 centimeters, and then I draw an arc to locate B prime, which is at this position. Now if you get measure the O2 B dash and O2 B, from these I can get the crank and coupler lengths, so which is what I have done. It turns out this particular design, L1 is 30 millimeters, L2 is 17, L3 is 44.5, and that 17 and 44.5 came from that O2B and O2B dash. And of course L4 I have chosen to be 50.7. Here's an animation of that. Let me open and show you the animation of that. Now we are moving away from the extreme, and that's it. So, all right. Now, on the other hand, I could go ahead and pick a point B, which is basically at infinity. So that means the coupler length essentially has become infinity. So the infinite length can be treated as a slider. So in this case, we arrive at the crankshaper mechanism, which is an inversion of the slider crank mechanism. The crank size happens to be, cannot be arbitrary, but is given by the distance between the fixed pivots O2, O4 multiplied by sine of theta by 2. So let me show the animation of this. So here is the crankshaper. So you can see that, watch the rocker, the magenta one. So that is the top extreme that it has gone down to, and now it is coming back. The angle between those two extremes happen to be theta or alpha, as the case may be. In this particular case, both are equal. So we have theta equal to alpha. So which is now it is coming off the lower extreme. And so the rocker rocks between these two extremes, and it's basically a crankshaper mechanism. And you could see that the angle between the two extreme positions that the green line makes is also going to be equal to theta or alpha, as the case. In this case, both are identical. All right. So the summary of what we have done so far: we have synthesized crank rocker using two approaches for a given theta and alpha, given theta between two extremes. We also defined alpha, which is the position angle between the two extreme positions made by the crank coupler line. The first case, we fixed O4 and chose a rocker length as the initial choices, and then we found that we could choose O2 on a circle. There were some regions of the circle which were not allowed, which violated the Grashof condition that the rocker has to be on the same side of the line joining O2, O4. That was one approach, but the flip side of that approach is O2 is floating. It can be anywhere, and sometimes it may not be convenient to use that approach. So instead we do an approach where we fix O2, O4 and then select, so we fix O2, O4 and then we drew semicircles based on which we located B1 dash and B1. And so based on this, we could come up with a rocker length, and once the rocker length was set, we could come up with the crank and coupler length. The time ratio, which is the ratio of the forward stroke to the backward stroke, can be controlled by the angle alpha, which is the angle between the crank coupler line for the two extreme positions. If alpha is positive, we get a quick return mechanism, which means the return stroke is basically done faster. The time ratio is greater than 1. Now alpha negative simply means that the forward stroke is faster than the return stroke. And of course the special case is alpha equal to 0 corresponds to a 1:1 crank rocker case. We have also discussed special cases when alpha has a relation to theta, which is theta by 2 or theta, and then we have seen what happens in those particular scenarios. All right. So let's, the one last topic before we close this, in the design process, we also worry about something called a transmission angle. So the transmission angle is nothing but the angle between the coupler and the coupler, which is the blue line here, and the output rocker. So this is an important parameter from a force transmission, torque transmission perspective. The ideal angle should be 90 degrees, which makes the torque transmission very easy to do. But we all know that that angle is not going to be constant. So there are some guidelines which are developed. We will not get into detail as to why that should be that particular number. The guideline is basically 90 plus or minus 50 degrees. So which means we want the transmission angle to stay in a range of 40 to 140 degrees. Now if it goes well below that or well above that, then we need to redesign our crank rocker so that the angles stay within 40 to 140. So I leave it as an exercise. I have given you a couple of dimensions, the designs that we have made. I want you to check out, at a few positions what the transmission angle will be. Now, if you have a slider instead of a 4-bar mechanism like this connected to the coupler, it is basically the angle between the normal to the direction of sliding and the coupler. So that's the definition of a transmission angle for that. All right. So what next? We move next to in the next lecture to path generation and rigid body guidance. We'll also briefly look at coupler curves. I'm not going to get very deep into the coupler curve atlas as it is. I will use an animation to basically show the various coupler curve shapes and how you could use this in order to do path generation, for example, right? So I mentioned that path generation is actually a special case of the coupler curve. So we will come back and look at that in the next video.